We have seen how to define and how to evaluate the double integral over a rectangle integration domain. Now, what if the integration domain is not a rectangle? Consider the integral over d of a function fxy dx dy, where the set d is not a rectangle, say something like that. We will consider only sets that are bounded, and the boundary of this set consists of a finite number of simple closed curves. Then, as we know what is double integral over a rectangle, we can think of a large rectangle such that the set is subset of this large rectangle. And then we define a function g, which will be defined in two ways. It is equal to f if the point xy is in D, and it is equal to 0 otherwise. And then we can define the integral of f over this set D as the integral over the Cartesian product AB CD, where ABCD is this large rectangle, of the function g. This is the definition. We usually don't use this definition for computation, but it's good to have some nice, good definition for the integral of a function over non-rectangle region. Now let's have a look at some properties that can be used to compute the double integral. First, if we have two functions, say f and g, not this one, just completely new story. And we multiply one of them with some constant alpha and the other function with some constant beta, and we integrate over some set d. Then, no big surprise, this is equal to the linear combination of integrals of f alone and g alone. So this will be alpha times integral of f dx dy over d plus beta times integral of g. And then, if the set D can be decomposed into a union of two sets, and if the sets are either disjoint, that means they have an empty intersection, or the intersection is just a finite number of points or curves, no fat sets, then the integral over the union is equal to the integral over d1 plus integral over d2 of some function. This is important that the intersection is not fat, because if you consider these two sets, d1, d2, then adding the integral over d1 and the integral over d2, then in the right hand side, this contribution would be there twice. While integrating over the domain would consider only these three parts, each just once. So for this, it is important that this does not occur. The two sets, d1, d2, may be either completely disjoint, that means empty intersection, or the intersection may be just one point, or a finite number of points, or one curve, but not some fat region.